Welcome to this episode of Gov School Rocks, where we learn how to speak rock and we learn to try to hear and understand what the environment is telling us about itself and its story. Today we're going to talk about sedimentary rocks. And as you walk around here in the Shenandoah Valley, this is mostly what you see. We talked about igneous and metamorphic rocks, both of which are crystalline rocks, sometimes referred to as the hard rocks. Sedimentary rocks are weathered products of other rocks, including sedimentary. Think about the rock cycle. Any rock can become another rock under the right conditions. So these can be metamorphic rocks or igneous rocks that are broken up into sediments, and then the sediments become compacted and then lithified, which is essentially lithification is whatever process is gluing those sediments together. So as an example, here is a sediment. I happen to have a spice rack or sediment rack where I keep sediments that are of interest to me. And I can take this sediment, which happens to come from Rathlin Sound, Giant's Causeway, which is actually in Northern Ireland. So this sediment here, and I have all of these gigapanned, and I'll share those with you in more detail. You can see what a sediment is, though. Sediments can be everything from little bits of mineral material, quartz and so forth, like you're used to seeing at beaches, sand, in other words, or little bits of shell fragments. Now, the shell fragments are going to break down pretty easily, and they may not last that long. The mineral bits break down as well. So if I take a basalt, which is made up of olivine, and excuse me, and then I break it down through the primary way to break down a basalt is through oxidation, and it turns into other minerals. The same with feldspars. In that case, it's hydrolysis. If I weather these materials down, the one thing that's going to remain at the end of that sediment originally is any quartz that's in it. That's the one mineral that's going to be more resistant to weathering than any other because of its crystal structure and so forth being what it is. But these can break down to the point where they go away completely, or they can break down to the point where they get compacted and lithified into the sediment that's made out of this stuff. And that's what a sediment is, though. But a sedimentary rock always starts off as weathered material. No matter what the situation is. So we have a lot of different sediments here, and normally you'd get a chance to see all of these in class. You'll get to see them all online, or at least get access to them because they've all been gigapanned, and where you can zoom in really, really close and get a good idea. It's really fascinating to look at a sediment. I mean, you're essentially looking at the broken bits of what was once a rock. And when I look at a rock like this, I mean, I get excited and I kind of know what's going on here. But the first time you look at a rock like this, it's just a rock. But there's a lot in that rock that's yearning to share a story with you. It wants you to know its past. And sometimes the way we know that is through sediment. Okay, so first of all, it's important to make a distinction between what is sedimentary rock and what is not sedimentary rock. There are some anthropogenically derived sedimentary rocks, like this one here. This is concrete. Another example is asphalt. When you think of blacktop or asphalt, most of that is actually quarried limestone. And about 10% of it is the actual tar that they use to glue the limestone together. It's actually what gives it its color and so forth. But these are not actually sedimentary rocks because we made them. A typical sedimentary rock, like a sandstone, or in this case, a mudstone like this, is made up of fragments. There can be a couple different types of rock. You can have a clastic, where you've taken chunks of other things and kind of cemented them together, and those can be both inorganic, like this one, this has fossils in it, but overall the material is inorganic of nature, inorganic in its origin. It's a sand or a silt in this case, derived from initially other rocks, igneous or whatever. Mostly quartz left over in here, just so small you can't see them. Or bioclastic, in which case you have like a limestone like this, full of fossils. And the entire rock actually is made up of what was once living material. Calcium carbonate in the form of mud that was originally part of the shells of forams or the shells of other invertebrates in a marine setting, ocean setting. Right? So this is a bioclastic sedimentary rock. And then you have sedimentary rocks that are entirely chemical. Here's a piece of travertine, and I've cut and polished one side of it. You can see there's kind of a layering to it. This comes here locally. This is deposited in Holman's Creek in Quicksburg, and this travertine is a result of the calcium carbonate That's the water being saturated with calcium carbonate in cave environments, karst environments, and it comes out onto the surface, and the carbon dioxide leaves, and then the calcium carbonate is deposited afterwards. This is sedimentary still, but it's a chemical sedimentary rock, so it's not clastic. It's actually either precipitated or evaporated. Like for rock salt, for instance, is another example. Rock gypsum, which we make wallboard out of, and so forth. If you've had sea salt, that's another example. That's an evaporite. So these are all, there's three main kinds, right? Bioclastic, just plain clastic, and then chemical sedimentary rocks. Sometimes the distinctions between the three can be a little bit shady. Like this could be bioclastic, but I primarily call it clastic. This is a mudstone. And I know it's a mudstone because the grains are really, really small. I can actually use my teeth and I don't get a whole lot of grit on there, so it's probably a mudstone. This is actually Mahantongo shale. It's not the best example of a shale breaking in sheets, but it's still that. This here is, I would call a mudstone as well. This is what's called banded iron formation. You can see the red oxidized iron in here. This was formed about 3 billion years ago on the seafloor and is actually a really important iron ore source in the Great Lakes region. This is indicative. This rock's story is really important to the story of life on Earth. Life on Earth originally was chemosynthetic, derived all of its energy from the chemical compounds it could break down in situ in whatever situation it was. Did not require sunlight, so you could have life forms all over the place, much as you do now at mid-ocean ridge vents deep in the ocean, where there is no sunlight, but where organisms are able to sort of subsist on things like hydrogen sulfide. Most life on Earth, though, that we're familiar with derives its energy from sunlight through photosynthesis. We, as humans, as omnivores, are living at what we call a higher trophic level, right? We subsist on organisms at lower trophic levels that ultimately are primary producers, taking sunlight and producing sugars and all the materials that that move up the food chain. And that allow us to exist. This rock is connected to that because at some point photosynthesis as a process had to evolve. It didn't just come out of nowhere. Evolution produced it. Organisms at some point were able to, had genetic mutations that allowed them to process sunlight and convert that into sugars. And as that process developed, more and more carbon dioxide was pulled out of the atmosphere and more oxygen was put into the atmosphere. But it wasn't actually the atmosphere first. First, it happened in the oceans. So carbon dioxide pulled out of the ocean water, oxygen replaced by oxygen as a byproduct. Eventually, the oceans become saturated with oxygen. And during that time, the iron-rich sediments in the bottom of the ocean that existed at the time were oxidized. And that's where this comes from. This is evidence of early photosynthesis going back 3 billion years. And that's really cool. So this is a pretty old rock with a great story to tell. Eventually the oceans became saturated with oxygen and the atmosphere began to accumulate oxygen as well. That came later on because there's a coupling between the atmosphere and the oceans. It's important to keep in mind as we think about biogeochemical cycling. This is also formed at the bottom of an ocean, but by that point, 380 million years ago, not 3 billion, life had evolved quite readily or quite handily. And you can see the little bit of a little shell fragment here. That's actually a brachiopod mold. And organisms like that were much larger. Here we're talking about single cell organisms, cyanobacteria, things like that. Here we're talking about, which aren't actually bacteria, by the way, they're algae. But here we're talking about much larger, higher organisms, as you will, if we think about the taxonomic lingo we use for that. Same with this one. This rock is 450 million years old and is entirely composed of organisms that originally somehow either subsisted on or themselves derived their energy from photosynthesis. And so this rock here is a poster child for everything we see in the environment going on right now in the marine realm. And they are coupled directly with biogeochemical cycling. These are calcium carbonate organisms, invertebrates, brachiopods, crinoids, bryozoans. These are all things that are extinct now. I mean, they have descendants that are still around today. And this was formed at the bottom of the seafloor, but pretty shallow actually. These organisms would have been in the photic zone, so within sunlight, we know that, and also within the wave, above the wave base, so not too far from the beach. Though in the Ordovician period, when this was deposited, there was nothing living on land, and still not enough oxygen for you or I to comfortably breathe in the air. It wasn't until a little bit later when grasses, vascular plants in particular, but algae also. I mean, there would have been algae living on land, but that's about it. Little gooey mats of things. Eventually, plants evolve further and begin to move out onto land once they produce vascular stems that can move water up against gravity and hold themselves up against gravity. Trees, ferns, fungi, all kinds of things evolve. The fungi don't have to be photosynthetic, but all these things evolve later on, and then land begins to be colonized by animals eventually too. But these animals were stuck in the ocean. Eventually, here's another 450 million year old rock. This time I cut it and polished it really nicely, and you can see that what's cool about sedimentary rocks, they tell you something about the environment. So this particular rock, was formed in an environment with lots of wave action. There's very little mud left in here. Most of the mud's been winnowed out and taken downslope. In this case, this rock came from further downslope, below a place that's usually below wave base, even during storms when the wave base gets lowered. As you make the waves bigger, the waves get bigger this way too, in those situations. But you can see there are layers, a layer of shell hash in here, and if you look closely, you can see the cross section of little shell bits and so forth in one little layer. So at some point big enough to winnow out and concentrate some shell material, or, this is a better example, a better explanation, this came from a submarine little mini landslide that came from further upslope and was deposited here, and then afterwards just the usual background sedimentation began to accumulate as well. So there's a story here to be told, and a very interesting one. There's broken clasts in here and other bits of shell fragments to tell that story. Finally, we get to another biochemical or so more like a chemical or biochemical rock. This is coal. I don't call it clastic, even though technically one could make the argument that it is clastic. Coal itself is made up of things called mackerels, like rocks are made of minerals. And so from that perspective, it is an agglomeration or a gluing together of things, of bits. Coal, though, are the coal deposits that we burn for electricity that are part of the big cause of global warming and so on, were formed in swamps that existed as Pangea was coming together, as Europe, North America, and Africa came together, and that ocean, that proto-Atlantic ocean, we refer to as the Iapetus Ocean, began to disappear, and tons of swamps all along the eastern seaboard existed at that time, 250 million years ago. This is Pennsylvanian coal, or during the Carboniferous period. Globally, we refer to it as the Carboniferous period. Here locally, the Mississippian and Pennsylvanian. But this is Pennsylvanian coal, which is really common in West Virginia and Pennsylvania and other places, New York, and all the way up into Canada, all along the Appalachians. So this coal, of course, is very economically important. Coal is a concentration of plant material primarily that was deposited in relatively oxygen-poor or oxygen-free environments in the bottoms of swamps, which still exist today. You could have other little bits of organisms in here that you're not even aware of, little bits of insects and so forth. Coal mackerels also tell you something about the pressure and temperature environment of the coal formation, because that coalification process is based on pressure and temperature as well. Coal can eventually have so much pressure and temperature that it goes from peat, humic material, just like the stuff you see falling off of trees and so forth, to peat, to lignite, brown coal, very common in places like Germany, to subbituminous, to bituminous coals, to anthracite. As you get closer to anthracite, you're getting more and more of the volatile material being forced out, and purer carbon remaining. So anthracite burns very hot, very cleanly, relatively cleanly as far as coal is concerned. There's just not as much of it. It's still dirty and still produces lots of carbon dioxide. But the mackerels in the coal can tell you something about whether there was a forest fire there at some point, or swamp fire, or whatever the case, and things like that. It's a pretty esoteric field of study. And I don't know of anybody who specializes in coal mackerels these days. I think it was more of a thing back in the 1960s and 70s, but it's still interesting. Okay, so those are sedimentary rocks. Sedimentary rocks have one other big, really, really important thing for us to consider, and that is every single one of them has a story that directly interfaces with the environment around us, and that we directly interface with. Whereas our interface with igneous and metamorphic rocks may be more indirect or more several steps away. Sedimentary rocks are all around us, and we're walking. They're kind of like the dirty skin of the earth, but that dirty skin of the earth has a lot to tell us about the environment and how it's changed, not only currently, but over time. So, this travertine was formed over the last maybe 150 years in Holman's Creek. During that time, these little layers have a record of oxygen isotopes that we can then pull chemically out of here. So we can do some stable isotope analysis of the layers in here to say something about the climate, particularly the moisture in the climate. Oxygen isotopes tell us something about temperature. They tell us something about moisture. These rocks you can still get oxygen isotope data from these, but it's much more ancient and much more coarse. But these rocks tell us something about a local environment that existed 450 million years ago. And I mentioned storms, hurricane-like storms. Yes, they occurred back then, and these rocks are part of the evidence for that. So the point is that when we think about James Hutton's ideas of uniformitarianism, the present is the key to the past. We look at present processes to understand how past processes occurred. And that's one of the big and powerful assumptions we have in the geosciences, and really in the environmental sciences, is that we can look at current processes and say something about how they occurred in the past. And that's really, really important. Each rock has a facies, which is, of course, all the characteristics of that rock. But those characteristics not only tell us what kind of rock it is. I mean, honestly, telling you this is a sedimentary rock is only somewhat useful. Telling you it's a limestone or a mudstone is a lot more useful. It's a lot more descriptive. Telling you it is a laminated mudstone with a layer that approaches a grainstone or a grainstone, but a packstone, and contains specific fossils, maybe a graded bed. These are things that are part of the facies of the rock that tell its story. What is the story that this rock is yearning to share with us today? What does it want us to know about its formation and what the environment was like all those years ago? And so that's what we're trying to do here. It's important to note that what we see going on in our environment today is only a snapshot. It's just at the moment, right? And we have 4.5 billion years of Earth history to understand, to really contextualize our current environment. And that's why it's so important to have some background and understanding of foundation in geoscience concepts, because these are the ones that provide the foundation for everything we understand in the environment. And again, they show us the evidence, the processes. This is the results of the biogeochemical cycling of the CHNOPS elements. And we'll look at those individual cycles also in this class, but those CHNOPS elements, how did they get where they are? How are they in the proportions that they are in the environment? How did they get there so that we can live and we can survive and the organisms around us can survive as well? There's an astronomical connection too, I haven't mentioned yet. Some of the elements, the trace elements in here, things like uranium and so forth, are really big ones that we also rely on and that are part of us also, come from stardust initially. You can't produce uranium on Earth. You can't produce gold, silver, platinum, and all these other elements on Earth. They had to have occurred in supernovae explosions, millions of supernovae explosions, and the accumulation, the aggregation of those minerals was all part of the planet formation process. There's a whole world out there. We are made of stardust. We are made of dust, dirt, soil, and how those materials then, these Earth materials then became us, became the biosphere around us. That's the story that the geoscientists have to tell us, or the rocks themselves, the materials themselves have to tell us. And as earth scientists or environmental scientists or geoscientists, whichever term you want to use, that's our goal, is to understand that story. All right. Until next time, have a great day.